in the previous classes, we have seen various kind of gate questions regarding 6th unit, right? Okay. So now in today's class, we'll start with the 5th unit. So before this, so in the starting of the classes, we discussed various kind of topics, right? So like if you generalize, if you take the first unit, second unit and third unit, they are mainly concentrating on how to create a conceptual schema and then how to implement that conceptual schema in the database. We can simply call it as physical schema, and to implement this physical schema we require a concept of SQL, right? How this SQL is working in the database, for that reason we try to study relational algebra and relational calculus, right? This is what majorly your 3 units are concentrating, right? And then we have seen one more unit, that is 4th unit, that is normalization. The main reason why we moved for normalization is to improve the performance of the database, right? So performance of the database in terms of storage capacity, like that, right? So how can we improve the performance of the database? By simply reducing the redundancy, right? How we are going to reduce the redundancy? All those things we have seen in your 4th unit. And then we come across with 6th unit. In the 6th unit, we are going to concentrate on to improve the accuracy of the database, and to access this database by multiple users. I mean, when multiple users are trying to access our database, they has to get exact data. They have to produce accurate results, right? So for that reason, we try to learn your 6th unit, right? So basically, if there is no concept of 6th unit, what will happen? Your results might be inaccurate if multiple people are trying to access one data item called A. If multiple people are trying to access at the same time, they may get inaccurate data, right? I don't want like that. I want to get the accurate data, at the same time I want to access by multiple people. For that reason, we studied transaction control management unit. Okay. Now in today's class, we'll start with one more unit. We can call it as indexing. What is the meaning of index? Have you anywhere observed that what you call index in the records, right? So what is the advantage of maintaining the index page? Searching is very easy, right? If you would like to move from one page to another page or one experiment to another experiment, by simply looking at the index page, we can just directly jump it to respective page. If there is no index page and you don't know exactly where the exact experiment is available, then what you have to do? You have to do compulsory page by page search, right? So to overcome the drawback, we are going to have index page, right? If you are able to observe, if I say this is a kind of a record book where it contains experiment 1 and page number 1, 2, 3, 4 and experiment number 2, 5, 6 and so on, right? And assume that there is no index page. Then what you have to do, if you want to move to some particular experiment, and assume that these experiments are also in some random order, experiment number 3, then experiment number 2, 5, 6, 7, 8 and 9 and so on. Now if somebody asks you to open the experiment number 2, what you will do? You know that your experiments are not there in the order, then what you have to do? Definitely you have to move by page. So trying to take the page by page is going to take more time or not? For example, if it takes 1 second for each time, then definitely it is going to take 9 seconds to access the experiment number 2, right? So is there any chance to reduce this 9 seconds or not? That is what our concept here, meaning that indexing is mainly concentrating on to increase the response to the user. To increase the response to the user query, we are going to perform indexing. To increase the response to the user query, we are making use of indexing, right? So what might be the solution to reduce the time from 9 seconds to less than 9 seconds? One thing is you need to arrange the record book in sequential order, in some sort of order, right? So like experiment number 1, 1, 2, 3, 4 and experiment number 2, 5, 6, 7, 8 and experiment number 3, something like this, right? So experiment number 3 or experiment number 2 should be 9, 10, 11, 12, and experiment number 3 should be 5, 6, 7, 8, and so on. And so on, right? Now, if somebody asks you to go for, can you go for the experiment number 2? What you can do? Can you jump directly to experiment 2 again? So, as the pages are not in the order, you may not get the exact data. Right? So, for that reason, what you can do now? You can simply make use of some kind of index. You can write some kind of index, right? I can call this as index page. Index page, what you are going to maintain? You are going to maintain simply experiment number followed by its reference. I can call it as its reference, right? So, for example, experiment number 1, page 1, experiment number 2, page 9, experiment number 3, page 5, and so on, right? If I say this one, now can you able to get the response somewhat better compared to earlier one? No, no. Right? So, this is what generally an indexing refers to, right? So, if somebody asks you for you to define, open the page number, experiment number 2, you can just go for the index page, and in this index page also you will go with linear search again, or you can go with binary search. Why you can go with binary search? Right, as they are here, they are in some string format, but in reality they are going to be some kind of keys, right? So, if the keys are in sorted order, if assume that these are the keys, and you know, right, so this is a kind of index page, as they are in sorted order, what we can do? You can apply some kind of binary search algorithm. When you are going to apply the binary search algorithm, it is going to take the log n base 2 time complexity, right? Meaning that every time I am going to skip half of the elements of this element. So, this is what you can simply call it. Now, once we reach it to experiment number 2, by applying the binary search algorithm, you can go for its reference page. What is the reference page? Page number 9. Directly can go. Right? So, this is a kind of simple generality. Right? So, in the coming class, we will try to explain the complete indexing concept. Okay, now fine. So, basically, this indexing concept is used for to give high response to the user query. We are moving for simply indexing. Right? So, basically, if you are able to observe, these entire things are going to be stored in the memory. Am I right or not? Right? So, whatever the data it might be, so your data is going to be saved in the form of tables. Your data is going to be saved in the form of tables, and all these tables are available in your memory. Right? If you take the memory, all your tables are going to be available in the memory. If you observe, this is a kind of memory. It contains again chunks of pages, where every page can contain again a collection of tables. This is what actually a memory look like. Right? Memory means simply a collection of data. A collection of data. Based on its behavior, it is going to be classified into different kind of things. One is a kind of primary memory, which you heard this terminology earlier. Another kind of one is secondary memory, right? Is database will be comes under primary memory or secondary memory? Secondary memory. Why it will be comes under secondary memory? Because your data will be permanent, right? If your data is going to be permanent, if you want to store the data permanently, then it will be classified under secondary memory, right? So, I can call this as non-volatile memory also. Volatile means temporary, which will change directly, right? Non-volatile means which may not change even the power is off, right? So, simply you can say that secondary memory means even when power is off, your data is not erasable. Your data is not erasable. I can call that secondary memory, right? The exactly opposite to this one is a primary memory. Primary, right? Meaning that when power is off, definitely your data is going to be lost. Definitely is going to be lost, right? But which one is the best one in terms of performance? Primary memory is the best one, because when you want to process something, you have to have your data should be always in the primary memory, right? If you are able to observe its structure, basically you are going to have hard disk or database or whatever it may be. It can be any kind of secondary storage device, which can be SDD also. SDD means it's not SDD, it is something like SSD, solid state drive, not secondary storage device. Solid state drive. Solid state drive is also one kind of secondary storage device, right? But our laptops contains what? Also contains secondary storage device, but what we can technical call as hard disk, right? So you have to know the difference, right? SSDs provide far more performance than the hard disk. SSDs, secondary storage device, contains one kind of a device called solid state drive, right? And if we take here, this is a main memory. I can call them as primary memory also, primary, right? So when your CPU is trying to work with certain data, called xy, and assume that this xy is available in hard disk, So for your understandability, I am trying to write this as hard disk, or I can call them as magnetic disk also. Hard disk I can call it as hard disk, right? Your xy is available in magnetic disk. Now, in order to work with x and y values, where it need to get, they has to compulsory get it to the main memory. Otherwise, it is not possible to process it, right? So meaning that if CPU wants to work with anything, it has to be available in the main memory, right? If it is not available, it will go to the magnetic disk and it has to get, and then it will work on it. This is what general, right? So for example, if I say 50 milliseconds is going to take the time to access the main memory, and 100 milliseconds is going to take to access the magnetic disk. Right? At the worst case, if main memory is not available, then how much time it is going to take to access the x and y values? 200 milliseconds. To access the x, I need to take 100 milliseconds, and to access the y, I need to take 100 milliseconds. So totally 200 milliseconds are required to access the entire data. Right? Suppose for example, if the main memory is there, right? First, whatever data that is required is going to place in the main memory, then it is going to work on it. Okay, right? For example, for this particular thing, it is required 200 milliseconds. For example, if one more time it is required x value, now at least this time also it is reducing the time or not. This time it is searching for x value. Yes, x is available here itself. Then there is no need to move for the hard disk again, right? So now the total time it is going to take as 250 milliseconds in order to access the values of x, y, and x, right? But if there is no main memory, it is going to take 300 milliseconds. Am I right or not? Yes, right? This is what the general concept of how your memory is organized, right? So if you look into more in depth about this, basically, if I say, if you would like to store your data, you can store your data in the form of registers also. Have you heard the terminology of registers? Right? Register is a kind of small memory location where it can store the data of I think around 6 to 64 bits of memory only. 6 to 64 bits of memory only. That's the reason we are not going to use the registers actually. Right? There are very kind of small applications where we are going to use, but it is going to have more high performance registers, followed by you have a cache memory, and followed by you have a main memory, right? So you know the meaning of cache memory. I can call as a RAM. Specifically, if I call them as static RAM, main memory I can call it as DRAM, dynamic RAM, right? And if you take the another level of the things, we can make them as magnetic disk. Magnetic disk, right? Magnetic disk means simply hard disk, right? And if you observe the another kind of things, something like optical disk is there. Optical, they are going to work with the lasers, right? So you have this idea in your IT, right? Optical disk and something like magnetic tapes if you go on writing like this, you will get various kind of different type of memories are there, right? So we can simply call this as memory hierarchy. Memory hierarchy, right? So basically, if you would like to evaluate these memories in terms of various parameters, we can able to evaluate one in terms of how much space they are going to be taken. They are going to be taken. What is the size? We can say space will define the size also, right? And if you say in terms of performance wise, which one is going to be more performance, and in terms of cost wise, which one is going to be more cost, right? If I try to say in terms of size, which one is going to have very less size? Registers is going to have very less size, then cache is going to have somewhat better size compared to registers, memory is going to have somewhat better size compared to cache, like that, right? Meaning that your size is going to be very less when you are going to move from top to bottom, right? If you observe, like the symbol here indicates that when you are going to move from top to bottom, size is going to be increased. Size is going to be increased. If you want to avoid the confusion, I'll write here. Your size is going to be increased when you are going to move from top to bottom. What about the performance? Performance is going to be increased or decreased? Performance is going to be decreased. That's why I have written up arrow, right? I am trying to say all in terms of top to bottom. Am I right or not? When you are moving from top to bottom, its storage capacity is increasing. That is what first point. And second point is performance is going to be reduced because it is going to have huge data. Trying to search data from the huge data is going to be more time. That's why its performance is going to be decreased. That's why I have written in the opposite direction. And what about the cost? Increases or decreases? Cost is decreases. Cost of the memory is going to be increases. Okay, here we have to take only one particular point, right? Cost of the memory is going to be decreases when you are moving from top to bottom. When you are moving from top to bottom, because cache memory is going to give more performance. When it is going to give more performance, it is going to have highest priority and it's going to be very high cost. It is going to be very high cost, right? Yes. So cost is going to be decreases when you are going to move from top to bottom. You have to understand this one, right? So here SRAM means cache, right? So if you want your understandability, so if you open your mobile, the frequently accessed apps will be available, right? Right? Those will be called as simply cache memory, right? But if you remove the cache memory and when you are trying to open one particular app again, you may observe some kind of minute time taken, right, to open the particular application. It may take some time, but instead of taking from the cache memory, right? That is the difference between cache memory and main memory. Right? So if you are able to observe, if I would like to include one more kind of memory, I can call it as cache memory. Now tell me what will happen here. Your CPU wants to access your data. First, where it is going to search? It is going to search in the cache memory. If it is not available in the cache memory, it will try to take it from the main memory. If it is not available in the main memory, then it is trying to take it from the hard disk or from the secondary storage device. Suppose for example, if it is going to take the 10 milliseconds of time to access the cache memory, then you can be calculated in different ways, right? So for example, if I try to observe, if you would like to access the value of x and y, first where it is going to search, it is going to search in the cache memory. If it is not available, it is going to go for the main memory search. If it is not available, it is going to go for hard disk or magnetic disk. If it is available at one particular location, it is going to simply reuse that particular component, right? This is very good. For example, if all x and y are available in the cache memory, then what will be the time complexity of our cache memory? 20 milliseconds. For accessing x, it is going to take 10 seconds, 10 milliseconds. For accessing y, it is going to take 10 milliseconds. Total 20 milliseconds. For example, if it is available in the main memory, it is going to be 100 milliseconds. If it is available only in hard disk, it is going to take 200 milliseconds. Like that is going to be calculated. But sometimes there is a chance of getting your data might be available. Part of the data might be available in the cache memory. Part of the data might be available in the main memory. Part of the data might be available in the hard disk. So at that time, it is going to take some kind of random calculation. It's not exactly random calculation. It is going to be calculated in different scenarios, right? For example, if I say that the time taken to access the cache memory is 10 milliseconds and whose hit ratio is J percentage. J percent means what? Out of the searching data, J percentage amount of time your data might be available in cache memory. If it is not, meaning that data might not be available, what might be its remaining ratio? 1 minus J percent. Am I right or not? And in main memory, for example, if I say that this is K percent, can you able to write some formula for this? I will try to write down. Try to observe. For example, if my searching data is available in cache memory, right, meaning that it is hit. Whatever data I am searching, it is available in the cache memory. As it is available in the cache memory, what might be the percentage of success in J percent? Then definitely how many milliseconds it is going to take? 10 milliseconds. For example, if I say this is C, this is M, this is P, right? So J into C milliseconds of time it is going to take. If my searching data is available in cache data, sometimes your data might not be available in the cache memory. Then what might be the ratio for non-success? 1 minus J. If it is not success, your data might be available in main memory or your data might be available in the magnetic disk. So for example, if data might be available in main memory, then what is the chance of getting it? K into what is the memory access for main memory? M, right? Can I directly write M here? M, or do I need to include C also here? You need to include C. Why you need to include C? Because we already spent some time in searching my required data on the cache memory, right? As I wasted that time, I have to include that time also. K into C plus M. If here also in memory also it is not available, then it will be 1 minus K into I already wasted time on cache memory, I already wasted time on main memory, and then I am trying to spend now some time on hard disk. This is the corresponding formula or how much time it is going to take in order to search for your required data. Hope you understood this one, right? We can simply call it as effective memory access time. Effective memory access time. We can simply call it as EMAT. Effective memory access time is the hit ratio of cache memory is J and time taken to access the cache memory is C. Failure rate of cache memory is 1 minus J, then the remaining thing and so on. This is what we can simply call it as effective memory access time. Okay, now fine. So basically here we are trying to think about the indexing concept, right? Indexing means what? Basically our data is available entirely on the hard disk. Your indexing should also be in hard disk only, right? If it is available in the primary memory, what will happen? It is going to be erasable, right? So it should not be available in the main memory. It should be always in the hard disk, right? So here we are trying to think about how hard disk is organized first, right? So if I try to think about the magnetic disk, how it is trying to store your data, right? So if I are going to simply observe, the magnetic disk is a collection of various kind of platters. It's a collection of platters. Platters means simply a kind of, in our terminology if I say, it's a kind of a CD. I hope you have the idea of CD, right? So it's a collection of CDs. All CDs will be together. We can call it as simply a hard disk, right? If you are able to observe, basically your hard disk is going to be look like this, right? It's a kind of rectangle shape. It will be of some size, right? It only contains a collection of platters, and these all platters contains the internal one space is there, because there has to be, it look like a kind of cylinder actually. It's a kind of cylinder, right? And again, they are all going to be connected via one kind of shaft we can call, and these are we call it as arms, right? So these arms are meant for, we can call them as arm. These arms are meant for to perform read operation or to perform write operation. These arms are going to be moved from towards right side or towards left side on a particular surface, right? So you can have two surfaces. If you observe, this is a kind of a platter. This platter having two surfaces. One is top surface, another one is invisible one, that is bottom surface. On both sides you can able to write as well as you can able to perform read operation, right? So every platter having its own arm also, right? So this is a kind of hard disk. Right? If you look into more in depth about one particular platter, if you observe, this is a platter. Actually, it's a kind of a round shape, and it's going to have exactly it will be equal sized, okay, no? Right? So for example, if I say this is a kind of a platter, this platter is divided into number of tracks, right? So this one I can call it as one track, I can call it as track 0. This one I can call it as track 1, and if I try to divide again, I can call this as track 2, and I can go on like that, right? So in between we have a shuffle, right, where as it needs to rotate the disc, it needs require some kind of support, right? So that shuffle it will be arranged in the center. Okay, fine. Again, to make them organized in an efficient manner, they have divided again this disc into sectors. Divide this into sectors, right? So you may get some kind of doubt. So here, how much amount of memory is going to be capable to store? That much amount of memory is going to be stored by this one also, because here it is going to have high density. As it is going to have high density capacity, it can able to have the capability to store as much amount of data that is going to be stored at the outer level, can able to store at the inner level also, right? So equal size can able to store. So this entire thing I can call it as one sector. So if I want, I can give the naming as sector 0 for understandability. So this one I can call it as sector 1, sector 2, sector 3, and this one I can call it as sector 4, right? Now try to observe, your data will be distributed over the entire this platter. Data will be distributed entire plot, right? For example, if I say starting from the inner circle, so I think this is a kind of shuffle, right? Supporter, that's it. So if I say here, this is 1, 2, 3, 4, 5, 6. Anyway, you can start 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. So multiple sectors are there now, right? So what is the naming of? So if you would like to move, to the 9th location. So if I say this is a kind of references, if you observe, so 9 is a kind of reference. If you think, if I want to move to the 9 reference, what might be its location name? Can I say track 1, sector 4? 9th reference location name is track 1 and sector 4. Yes or no? Right? So observe, this is what? Track 1. And if you observe this triangle shape, it will becomes under sector 4. That's why I made it as track 1, sector 4. What about the 17 reference? Very good. Track 0, sector 0. Track 0, sector 5. Okay, anyway, any kind of naming, right? So for example, if I say this is sector 0, this will be sector 5. Okay, it might be anything, right? Track 0 and sector 3. So this is the way your, so how they have, why they have split this into multiple things? Because again I am saying, because if they wants to, so this is a kind of hard disk. If they want to place entire thing in the main memory can have a size of maximum some kind of MBs, or depending upon your system capacity, it can have that much RAM size. But entire hard disk cannot able to place in the memory, right? Main memory. So at that time, what will do? They will try to split your hard disk into parts, right? Those parts will be like this. Parts will be like, for example, assume that this is enabled to store only 30 MB of main memory. The main memory capacity is only 30 MB. If you want to store, so assume that here each location reference can able to store 10 MB. Then what is the capacity of this entire platter? So total how many positions are there? How many references are there? 19 references are there, and each reference location I can able to place 10 MB of data. So total how much memory it is capable to store? 190 MB. Right? Is 190 MB can able to store in one particular main memory? No. It can able to store only 30 MB of memory. So for that reason, what they will do? What your algorithm will do? Algorithm will try to take the needed memory where it can able to store only 30 MB. So it can take, assume that it can take two consecutive locations, 11, 12 and 7. That's it. So it can able to place the 11th page, 12th page and 7th page. That's it. I mean 11th means what? Their data. That's it. So that's the reason, in order to make them accessing in various different ways, they have split it into various kind of different ways in terms of called as tracks as well as sectors. Right? Here some important terminals are required here. One is seek time. Seek time. So seek time means, for example, I am present at the 14th reference location. And the 14th reference location, which I can call as X. I would like to move to Y reference location. Y means what? 12th reference location. I mean, I am presently using the X data. I would like to use now Y data. What I have to do now? Can I directly jump to Y location? Is it possible? No. What you have to do? On this surface, we have a arm, right? We have arm. This arm is presently at X location. Now I need to move to this arm to first which track? I have to move track 0 to track 2. I need to move. Track 0 to track 2 I need to move. Then I need to rotate the platter. Once I rotate the platter, my Y will be comes to here. Right? Then I can able to access the Y value. So means what I am trying to do here, in order to access a particular data item, first I am trying to move to respective track. Then I am trying to then instead of saying the move, I am trying to rotate to particular sector. Then I am trying to access my required data. Right? This is what generally happening to access the data. Right? Then what is the meaning of seek time means here? So if you would like to access the data, you need to go to the respective location. So seek time means here the difference between the time taken from source track to destination track. So here this is what X, right? If you would like to move to this Y, I need to move to track 2 first. Right? The time taken to move from track X to track Y, I can call it as seek time. Simply I am saying that difference between source track to destination track, I can call it as seek time. And another one is rotational latency time. Rotational latency time means once I move from one track to another track, I need to rotate my platter now, right? So how many sectors we need to change? How much time it needs to take to move to exact data? That is what you can call as rotational latency time, right? Means time taken to move from source sector to destination sector. Source sector, destination sector, I can call it as rotational latency time. Sometimes you may observe rotational latency they may not give. Then you can consider the average rotational latency. Rotational latency means RTT by 2. Simply RTT by 2, meaning that rotational latency by 2, I can call it as average rotational latency. And another terminology here is data transfer rate. So I hope you are understanding, right? Seek time means moving from one track to another track. Rotational latency means moving from one sector to another sector. Data transfer rate means after moving to the respective location, you need to access the data. You need to send the data to the required location like main memory. So that is what you can call as transfer time. So how much time you are trying to take to send the data or to retrieve the data? We can call it as data transfer rate. Right? So we can define this data transfer rate in terms of seconds. For example, if I say for r seconds, my hard disk capacity is, for r seconds it can able to transfer z bytes of data. Then for 1 second, how many bytes of data it can able to send? Z by r bytes per second it can able to send. So data transfer rate you are going to define always in terms of single second. If somebody asks you to solve what is the data transfer rate, you have to define in terms of 1 second, right? Or sometimes you may define in terms of rotations also. I mean, if I say it is going to take r rotations in order to transfer z bytes of data, then to transfer k bytes of data, how many rotations it is going to take? I think just you need to perform the cross multiplication. Rk by z rotations are required, so z are going to be bytes are going to be cancelled. Okay, now so Rk by z rotations are required in order to transfer k bytes of memory. Right? So what is the meaning of seek time? Modulus of x minus y. Am I right? X is here, y is here. I mean, if I say this is x track and this is y track, or in terms of this terminology, if I say track 0 minus track 2, so value should not be negative value, right? So it should be positive value in time. So track 0 minus track 2, or I can say x and y are the two track names, x minus y is called as seek time. What might be the rotational latency? Again, you can say in terms of sectors, right? So sector 0 minus sector some sector p minus sector q, right? So if I extend this one, if I am saying that my platter capacity is 3600 rotations per minute. RPM means rotations per minute. My platter capacity is 3600 rotations per minute, right? So then for one rotation, how many milliseconds it is going to take? Hope you understood the question, right? If my platter capacity is 3000 rotations per minute, for one rotation, how many seconds it is going to take? What is the meaning of this one? Rotations per minute. Minute means what? 60 seconds, right? Meaning that for 60 seconds, they have taken 3600 rotations. 600 rotations. For 1 second, how many rotations? Or what they are asking here? For one rotation. They are asking for one rotation. So for one rotation, how many seconds it is going to take? So no need to calculate, right? 60 seconds by 3600 rotations, which is going to be 1 by 60 seconds. Am I right? 60 by 3600. 66 are 360. So 1 by 60 seconds. Right? Can you able to get into milliseconds? So for one rotation, how many milliseconds are taken? You know, for 1 second, how many milliseconds are there? 1000 milliseconds are there. 1 second, 1000 milliseconds are there. Then for 1 second, for 1 millisecond, 10 power seconds. 10 power minus 3 seconds, right? You can able to solve it, right? 1 by 1000 seconds. So 1000, if you take to the top, it will be 10 power minus 3. So for 1 second, it will be 10 power minus 3, right? So try to observe now. Right? So if you are able to calculate this one, can I perform 1000 by 60 into 1000 seconds for one rotation? Is it okay? Right? Now, if I take out this 0 and this 0, 100 by 6 is what? 6 1s are 6 6 are around 16.67. What is 1 by 1000 seconds? 1 by 1000 seconds is 10 power minus 3 seconds. 10 power minus 3 seconds. So I can write as milliseconds. So this is equivalent to one rotation. So for one rotation, it is 16.67 milliseconds it is going to take. So if my capacity of the platter is 3600 rotations per minute, how many milliseconds it is going to take in order to perform one rotation? 16.67 milliseconds. Okay, now. So these are some of the technical terminologies that you need to know when you are trying to solve any kind of gate questions. Right. So take a minute of time and try to observe if you have any doubts. Observe this one. So this is what simply a kind of a magnet disk. Okay, now. So the way your internal system will contain the hard disk, right? So this is what I can call as arm. This arm is moving from towards to the inner circle and this towards the outer circle. So the same arm is moving towards inner as well as outer. Right? Based on moving, it is moving like something like we can call it as tracks are changing, and once the track is changed to the required destination, it is trying to rotate along with its shuffle, which means I can call this as a shuffle. Based on that, it will rotate. Then once you reach it to the respective destination, it will try to read the data and it will send it to the respective location. We can call it as main memory. Okay, now. So based on these concepts, so here if you are able to observe, what is the meaning of access time? Access time of data. I mean, I need my entire data to read to send it to the main memory. For that, what I am trying to do, I am trying to perform track changes. I need to perform the track changes, that is what seek time, and then I need to perform sector changes. Then I can call it as rotational latency time. Then I need to send data transfer time. So access time I can simply call it as seek time plus rotational latency plus data transfer time. We can call it as access time. Okay, so note down one particular problem. So I am trying to split the question into the points only directly. So number of surfaces of the magnetic disk are 512 ohm. number of surface of the magnetic disk are 512, and if you take each surface, each surface is going to have 512 tracks. Each surface is going to have 512 tracks, and if you take each track, it is going to have 2k sectors, and if you take each sector can able to store 4096 bytes of memory. Given that average seek time is 30 milliseconds, RPM is 3600, then find out capacity of disk, find out data transfer rate, and then find out access time for one sector, right? Right. So guys, try to observe here. You can note down later. So if you are going to observe any kind of hard disk, this hard disk is going to have many platters. Among those, if you take one platter, is going to have two surfaces. One is top surface, another is bottom surface, right? So indirectly they are saying that they have given the one entire hard disk. They haven't defined any how many platters are there, but they said that the number of surfaces are 512, right? Number of surfaces are 512, and this surface is going to have 512 tracks, and it is again each track contains 2k sectors, meaning that each track contains 2k sectors. If you are going to split like this, it is going to be look like the earlier diagram only, right? And they said that if you take one track, one particular sector, this particular location can able to store 4096 bytes of data. 4096 bytes of data. Right? Now with this one, can I able to calculate the capacity of the disk? What is the capacity of the disk? So can I directly write the capacity of the disk is number of platters, and each platter contains two surfaces. Right? I can generally write number of platters, and each platter contains two sides of data into 2 plus each platter contains number of tracks, and is it a plus or multiplication? Multiplication, good, right? Number of tracks, and each track contains number of sectors, and each sector contains size of the data. That's it, right? This is what a capacity of the disk. But they have given here number of surfaces directly, right? So then what I can do here, this entire thing I can write as number of surfaces. What is the number of surfaces? 512 into number of tracks are 512. 2k sectors means 2 into 1000 sectors into size of data is 4096 bytes, right? So if you are able to solve this one, so this is I can write as 2 power 9. Can write as 2 power 10 is 1024. 2 power 11 is 2048, which is equivalent to around 2000. So can write this as 2 power 11. 2 power 10 is 1024, right? So for this, if you are going to multiply into 2, which is equivalent to 2 power 11, right? 2048. 2048 is nearly equivalent to 2000. 2 power 11. into 2 power 12. Okay now, equal to nearly to 2 power 12. So total is what? 2 power 9 plus 9 18, 18 plus 12 30, 30 plus 11 is 41. So 2 power 41 bytes of data it can able to store. That is the size of the capacity of the disk, right? So they may give in terms of again different formats again, right? So they may give in the form of bytes, bits, or again whatever it may be, right? If they have given the options in the form of bits, what you will do? 2 power 41 into 8 bits. Again they may give in different formats, right? So that you can convert. Right? Basically, if you are able to observe, 1 bit means what ma? It can be either 0 or 1. 1, right? If I take 1 byte means 8 bits. Okay. 1 nibble. This is important. 1 nibble equal to 4 bits. 1 kilobyte. 1024 bytes. Okay now. 1 MB. 1024 KB. 1 GB. 1024 MB. 1 TB. Terabytes. 1024 GB. 1 petabyte. 1024 TB. 1 exabyte. Peta, I hope you know. This will be peta. Exabyte. 1024 petabytes. 1 zettabyte. 1024 exabytes. 1 yottabyte. 1024 zettabytes. So like this we have various kind of measurements are there which I can know that, right? So now if I try to say that 2 power 41 bytes, 2 power 41 bytes in terms of terabytes, can I write terabytes, right? We are at this particular level, we need to write in the form of terabytes. So we need to convert everything into terabyte form, right? So can I write 1 KB as 2 power 10 bytes, 2 power 10 bytes, 1024 as here also 2 power 10, 1 KB as 2 power 10. Indirectly I am saying that 1 MB is 2 power 20 bytes. Similarly 1 GB, 1024 means what? 2 power 10. 1 MB means 2 power 20 bytes. So 1 GB means 2 power 30 bytes. So you can practice it, you can get the idea, right? So similarly if I write for 1 TB, 2 power 40 bytes, 2 power 40 bytes, right? So for this in terabytes, if I say 2 power 40 bytes plus 2 power 1 byte, right? So 2 power 40 bytes means what? 1 TB. So it should be into, na? Yes, it should be into, right? 1 terabyte into 2 power 1 byte value, right? So which is equivalent to 2 terabytes. So 2 power 41 bytes is equal to 2 terabytes, right? So similarly for the coming class, try to reference in the form of megabytes, gigabytes and petabytes. You can do it for the coming class. Is it okay everyone? Right. Next one is data transfer rate. What is the meaning of data transfer rate? You need to define in terms of second. For 1 second, how much data it is transferring, right? So for that, what you can do? So you require to calculate data transfer rate, that is also for 1 second. 1 second, right? So basically, according to my explanation, for r seconds it is going to take z bytes of memory transferring. Here they are asking simply for 1 second. For 1 second, it is transferring z by r bytes of data. Z by r bytes of data. Now, what might be the parameters you required here? What might be the parameters you required? The value of z you have to know. What is the value of z? Z means how much data you are transferring, right? So, do you know any kind of data related to the seconds here? Any kind of data related to the seconds here? So, do you know RPM? Right? RPM means what? So, here for 60 seconds it is going to take 3600 rotations. Then for 1 millisecond, how many rotations it is taking? Or if I say for one rotation, how many milliseconds it is taking? Which we already calculated earlier, 16.67 millisecond. 16.67 milliseconds. For one rotation it is taking the 16.67 milliseconds. So if I try to equate, for one rotation it is taking 16.67 milliseconds, which is equivalent to again one track. Am I right? Which is equal to one track. What is the capacity of the track? See, I don't know the values of r second and z seconds. I am trying to make it equate, right? So you know, for one rotation 16.67 milliseconds it is taking, and which is equivalent to again one track, which is equal to one track, right? Now, can you get the bytes? Which is equal to again bytes. So can I say for one track how much memory it is saving? For one track how many seconds it is taking? How much memory it is transferring? See, for one track they have given already how many sectors are there? 2k sectors are there, and each sector can able to store 4096 bytes, right? So simply I can write this as 2 power 11 into 2 power 12, which is equal to 2 power 23 bytes of data, which I can write as 2 power 20 into 2 cube bytes of data. 2 power 20 means 1 MB. 1 MB into 8 bytes means what? 8. So total, which is equal to 8 MB. So one track can be able to store 8 MB. So which is equivalent to 8 MB. So I think all these parameters are equivalent now. Am I right? Am I done? One rotation can be able to transfer 8 MB of data. 16.67 milliseconds is going to transfer 8 MB of data. Or one track is equal to 8 MB of data. Or if you would like to transfer 8 MB of data, how many milliseconds it is going to take? All those things. So can I directly write 16.67 milliseconds it is going to take 8 MB of data, it is going to be transferred. But what is our question here? For transferring 1 second. For transferring 1 second, what do you need to do? So now can you able to solve it? So simply 8 MB into 1 second by, I think I am writing the reverse, right? So you need to have, I am writing correct only, 8 MB into 1 second by 16.67 milliseconds. So try to calculate this one. So what might be simplification? So can write 16.67 milliseconds as 1 by 60 seconds. So earlier one we got it right. 16.67 milliseconds as 1 by 60 seconds. So 8 MB into 1 second in by 1 by 60 means what? 60 1 by seconds. Again these are going to be cancelled, right? So 8 MB into 60, 8 MB into 60, which is equivalent to 480 MB. So for 1 second it is going to transfer how much MB of data? 480 MB of data. That is what the meaning of data transfer rate. So for the second one, data transfer rate is 480 MB. 480 MB. Okay now. So you need to have perfect with the calculation. Okay now. What about the another one? So you need to calculate the access time. Calculate the access time. Access time is what? Seek time plus rotational latency time plus data transfer time. So seek time, you know, seek time they have given clearly mentioned as 30 milliseconds. 30 milliseconds. So you can write the seek time as 30 milliseconds. What might be the rotational latency time? Is there anywhere they have mentioned the rotational latency time? No, they haven't given. If they haven't given, what you can do? You can take the average rotational latency time. What is the average rotational latency time? 1 RTT by 2. Right? So what is 1 RTT? 16.67 milliseconds it is going to take by 2. What is data transfer time? Now, what do you mean by data transfer time? Data transfer time how much? 16.67 milliseconds it is going to take 8 MB of data. 8 MB of data, right? So what you are trying to transfer? See, here data transfer time is, it is simply nothing but representing in terms of second. Here indirectly I am saying that for 1 second I am trying to transfer 480 MB of data. That is for sure up to now. Here in terms of this particular thing, what you are trying to calculate is, you are trying to take the time for seek time, rotational latency time plus data transfer time. Data transfer time means how much data you are trying to transfer. Is it something like, I can say, if you are able to observe, each sector is how much amount of data it is taking? 4096, right? So that much amount of data you are trying to transfer. So for 4096, how much time it is going to take? So if you are able to observe, 16.67 milliseconds is going to take for to transfer 8 MB of data. 8 MB of data. I want to transfer here what amount of data? 4 KB. 4 KB is equal to 4096, right? 4096 bytes. So for that, how many milliseconds it is going to take? You can calculate this one. Tell me more. You can calculate this one. You will get around, so if you want I can calculate 16.67 milliseconds into 4 KB by 8 MB, right? So try to convert. I think bytes are going to be cancelled, and 4 KB. So can you tell? What is the next hour? Laser. So can you convert 8 MB into KBs? Right? What is the value of this one in the denominator? So 8 into 2 power 10 KB, right? So if I say 16.67, so you should not take this much time. 4 KB by 8 into 2 power 10 KB. KB is going to be cancelled now, right? 4 ones are 4 twos are, right? Now this will be 8.35, 2 8s are, 2 3s are, 2 3s are, 2 5s are. 8.335 milliseconds by 2 power 10. What is the value of this one? You will get around 0.0083, right? So 0.0083 milliseconds. If you are going to calculate, finally your answer will be 38.34 milliseconds. So the access time for the given hard disk is 38.34 milliseconds for a particular sector.